Assalamualaikum warahmatullahi wabarakatuh. Today's topic is about fundamentals of thermal radiation. So I believe that all of you already learn a basic of the radiation, just surface of the radiation, okay? But now in this topic, this is the last topic in the heat transfer and equipment, chapter 6, radiation. So in this chapter, we will actually focus more on how to calculate the emissive energy from a surface or from the materials itself. Let's go to the next slide. So the objectives of this study is actually, when you finish studying this chapter, you should be able to, one, understand the idealized blackbody. So we have in CPP you have or in thermodynamic you already have you already know about the terms ideal fluid or ideal gas, but now in this heat transfer and equipments we have ideal materials, the idealized blackbody. So which means that is the perfect perfect materials for the radiation. Okay, idealized concept, that is just only a standard. The blackbody is only a standard. Okay, idealized blackbody. And calculate the total and spectral blackbody emissive power. So these two terms is actually not very not have so many difference, since total blackbody emissive power, which means that we are calculating or we are trying to evaluate the emissive power from 0 to infinity. Whereas for the spectral blackbody emissive power, we are calculating blackbody emissive power at specified wavelength. For example, 0 to 100 micrometer. So that is the spectral blackbody emissive power. And second, calculate the fraction of radiation emitted in a specified wavelength band using the blackbody radiation function. So you will understand about this after this, okay? And then third, develop a clear understanding of the properties, emissivity, absorptivity, reflectivity, and transmissivity on spectral, directional, and total basis. So for radiation, we will need to understand about these four terms, okay? So we have emissivity, absorptivity, reflectivity, and transmissivity. So for the emissivity, the body will emit the energy, so emissive. And then for the absorptivity, once the radiation strikes to our surface, okay, to our material, and then some of that radiation energy will be absorbed by this material. Whereas for the reflectivity, some of the incident rays or strike radiation energy will be reflect on the surface of that materials. And the last one is transmissivity. Transmissivity is that incident rays will pass through to the materials. So normally transmissivity can be in the glass, not in opaque surface, okay? Because opaque cannot pass the light or incident rays through it. And then for the transmissivity, semi-transparent, transparent, or transparent materials, okay? The fourth is apply Kirchhoff's laws to determine the absorptivity of a surface when its emissivity is known. So after this, you will understand more on the Kirchhoff law, and a very simple law is actually. And then the last one, appreciate the importance of greenhouse effect. So because the radiation, we know that the sun emits radiation energy, and it will transfer to the earth. And then this radiation will create actually a greenhouse effect. Some of the rays is actually being reflects by the ozone layer, Not all the materials, not all the rays pass through to the ozone layer. Some of them will be reflect by the ozone. Okay, introduction. Unlike conduction and convection, so we know that the conduction, before this we know about the conduction, we know about the convection. Both of these mode of heat transfer requires mediums. Okay, medium in order to transfer the energy. For example, for the conduction, we are requiring solid metal or solid in order to transfer from the high energy to low energy. For the convection process, we are requires mediums such as liquid or gas, okay, for the convection to occurs. But in radiation, it does not require the presence of materials, medium. For example, like I said before, the sun will radiate energy, and that radiation will go to will strike to the earth. And we know that the space is in vacuum. So therefore, that radiation does not require any mediums to transfer the energy to the earth, okay, to the earth. And then what is actually radiation? So how does this radiation is actually radiates its energy, or the materials radiates its energy? So the theoretical foundation is postulated by James Clerk Maxwell, where that radiation is actually the electromagnetic waves or electromagnetic radiation. So represent the energy emitted by matter as a result of changes in the electronic configurations of the atoms or molecules. And after this, I will show you how that electronic configuration release an energy, okay, in terms of radiation. So the electromagnetic waves, okay, can be characterized by their frequency V or wavelength lambda. So lambda here, lambda is equal to c. C is the speed of propagation of wave in that medium, and divided by the frequency, okay, speed of light c, okay. So that is the equation to find what is the wavelength. And then this is how the electromagnetic waves produce. So we take a look at the first figure, where when a ground state electron is excited, it absorbs photons. So at the first state, at ground state, the photons here will be at this position, and after that it will excite in the excited state. So it will excite to another what we call here is another, it will excite to the another, what we call this okay, it will excite and absorb a photons. The energy of the photon is equal to the energy needed to maintain the electron at higher orbital. Okay, orbital. So first is at ground state, and then it will excite in excitation state, and it will absorb a photons. So when it absorbs the photons, that photons energy is equal to energy needed to maintain at this position, at this orbital. Okay, the last orbital, the next orbital, the electron will excite and it absorbs the energy, and then that energy is equal to the energy for this photon to maintain at the position of this orbital. And then when the electron returns to the ground state, okay, the excitation state is not the stable state, and then it will return to the ground state, and when it returns to the ground state, it will release energy. So that release energy is actually in the forms of electromagnetic waves. Okay, so here electrons are charged particles that can be produce both an electric and magnetic field. In order for electrons, however, to produce electric or magnetic fields, they must be in motion. A charged particle, such as an electron that moves back and forth, creates both electric and magnetic fields. The source of all electromagnetic waves is charge that is changing speed or direction. So it will emit the energy, okay? That energy is in terms of electromagnetic waves and photons, okay? So the electromagnetic spectrum is a continuum of all electromagnetic waves arranged according to frequency and wavelength. The sun, earth, and other bodies radiate electromagnetic energy of varying wavelength. So we take a look at here, we have so many different frequency here, and then each of these frequency have different radiation types wavelength. So for example, bleedings for the radio will emit about 10 to the radiation length wavelength is about 10 to the power of 3, and then we are using microwave we are the wavelength is about 10 to the power of -2, and then for the infrared 10 to the power of -5, and so on. But all of these radiation type, we can only see the visible light, okay? About infrared, visible and infrared, okay? Sometimes, no, we cannot see the infrared. We are only can see this visible light. That's why this visible light have different types or different colors. We have red, orange, yellow, green, blue, indigo, and violet. So each of these colors have different wavelength. Okay, so for the red, we have these kinds of graph, and then for the orange, these kinds of graph, and then when it comes to violet, we can see that there are so many peaks here. The waves is actually different from the red color. Okay, that is visible. So we can only see the visible light. Okay, a body at a thermodynamic. So this is the concept of blackbody radiation. Okay, a body at a thermodynamic or absolute temperature above 0 emits radiation in all directions over a wide range of wavelength. So which means that all the surface will emit radiation if the condition is if that body is actually above the 0, above the absolute temperature, above the absolute temperature. Okay, the amount of radiation emitted from the surface at a given wavelength depends on a material, the material of the body, and the condition of its surface, and then the second one, the surface temperature. So what is actually blackbody? In simple word, blackbody is perfect emitter and perfect absorber. So, but in real body, we cannot actually see that these kinds of blackbody exist. Okay, in real life, we cannot actually see that these kinds of blackbody exist. That's why I said before, blackbody is just a standardized or idealized concept of radiation. So it is a perfect emitter and perfect absorber. So it will absorb all the incident radiation and it will release all the radiation in its body. Okay, so we can see here in blackbody, the amount of radiation is uniformly. We can see this arrow. It will transfer the energy uniformly to the surrounding. Whereas for in real body, we cannot get this kinds of uniformity, and it will be a non-uniform. Since we know that the surface of the real body or the surface of anybody or any surfaces, we know that surfaces have its own surface roughness, and that surface roughness is actually will transmit this energy transmit this energy in non-uniform form. Okay, because of the surface actually. So surface will have its surface roughness, material will have different surface roughness. Therefore, we can predict that that the real body cannot behave like this. It will not uniformly distribute all the energies. It will be non-uniform. Okay. So the radiation energy emitted by black body per unit time. So this is the equation to find what is the black body emissive power. So we will use EB. E stand for emissive, B is black body at certain temperature. So depends on your temperature. If you want to find the temperature here at 300 Kelvin, therefore you will calculate the emissivity for the black body at 300 Kelvin. So you will use Stefan-Boltzmann constant times with temperature to the power of 4. So this temperature is the same as this temperature because you want to find what is the emissive power for the black body at 300 Kelvin. Therefore here T to the power of 4, this temperature will be at 300 Kelvin. So please remember the Stefan-Boltzmann constant is 5.67 times 10 to the power of minus 8 watt per meter square dot Kelvin to the power of 4. So actually the black body is does not wait. Okay, although a black body will appear black to the eye, okay, a distinction should be made between the idealized black body and ordinary black surface. So any surfaces, we know before this, we learn about that black colors because why does we have a black shirt, black purse and all the black colors? Because that black colors will absorb all the energies. But at this point, you cannot say that all the black color is a black body. Okay, since we know that the black colors absorb energy, and we cannot say that that black body is a black body, which means that the black in colors is not a black body, not necessarily a black body. Okay, for example, snow. Okay, we know that the snow, snow is one of the approximate black body. So snow, when the incident rays, which means the light strikes to the snow, we know that when the UV light strikes to the snow, it will reflect all the energy, all the wavelength, and it will create white in colors for the snow. But when we strikes with the infrared radiation, infrared types of radiation wavelength, so we will see that the snow is actually a black body. Okay, it will appears black for the infrared region. Okay, same with the white pane and large cavity with small opening. So this large cavity of a small opening is a black body, since we know that we have a small opening area here. So when we put the incident rays inside, and then that incident rays will strike here, and it will reflect the energy, emit and absorb the energy and emit the energy. Then that emission will absorb by this point. For example, here. So let's say we have this energy will strike to this point, and then this point will radiate energy, and it will radiate to this side, and this side will absorb all the energy, and then it will emits the energy, and then go to this point. Okay, for example, this point will radiate energy to this, and this will absorb totally, and then will emit totally. And then it will go at this point. All point in these cavities will perfectly absorb and perfectly emit the energy, and it will approximately that kinds of a situation, or that kind of phenomenon is actually approximate to the black body. Okay, for the spectral black body emissive power, so here previously we know that EB at temperature, and we will use these kinds of equation. So in order for us to find a specific wavelength, for example, we want to find from 0 to or we want to find a specific wavelength, for example at 300 micrometer, so we will use these kinds of information, these kinds of equation. So this emissive power for the black body at specified wavelength, for example 300 micrometer. So here 300 micrometer and temperature is 300 Kelvin as this, okay? And then we will use this equation. So you will substitute the lambda with 300 micrometer. So this is actually equation for the liquid, for the gas or vacuum, sorry. This equation is valid for vacuum and gas. But if you want to apply to the liquid, so you must make a modification to this equation. Where do you have to make a modification? You have to modify the C1 value here. So C1 value here must have C1 over, okay, for the liquid, you have to modify this equation into C1 over N. What is N? N is a refractive index, okay? Refractive index. Okay, by using that equation, you have to modify it a little bit in order for you to apply this equation into liquid. Okay, for the vacuum and gas, you just apply directly. Next, the variations of spectral blackbody emissive power with wavelength is plotted in figure 12.9. This is figure 12.9. So, the variations of the spectral emissive power, okay, several observations can be made from this figure. We can see this figure. We have wavelength here, and then we have emissivity, emissive power for the black body at lambda. So lambda is specified wavelength, depends on you lah. Okay, if you want to find the specified wavelength at 1 micrometer, then you have here 1 micrometer, and you will see what is the emissive, spectral emissive power. Okay, and we have a different temperature here, because from here we know that this functions is depends on the temperature. So different temperature will have different kinds of peaks or different kinds of graph. Okay, the curve will be different when we have different temperature. Okay, the emitted radiation is continuously functions of wavelength. So as we can see here, each of the graph depends on the wavelength. As the wavelength increases up to the peak, this graph peak of the graph, and then it will reduce. Okay, it is a function of the wavelength. Okay, at any specified temperature, it increases with wavelength, reaches a peak, and then decreases with increasing wavelength. Okay, at any wavelength, the amount of emitted radiation increases with increasing temperature. So as we can see here, different peaks for different temperature. So if we have high in temperature, therefore we can get a high peak point for that equation, okay, for that graph. And then as temperature increases, the curve shifts to the left to the shorter wavelength region. Consequently, a larger fraction of the radiation is emitted at shorter wavelength at higher temperature. So we can see from this figure, as the temperature increases, the peak here, the peak for each of the graph will shift to the left. Here, shift to the left, okay, to the shorter wavelength. So which means that at high temperature, we have a shorter wavelength for lambda maximum, okay, peak, this peak, maximum peak. As the temperature increases, the lambda maximum, which means wavelength, maximum wavelength will be decreases to the shorter wavelength. Okay, the radiation emitted by the sun, which is considered to be a black body at 5,780 Kelvin, so approximately 5,800 Kelvin, so reaches its peaks in the visible region of the spectrum. Therefore, the sun is in tune with our eyes. Okay, On the other hand, surfaces at T below than 800 Kelvin emit almost entirely in infrared region and thus are not visible to eyes unless they reflect light coming from the other sources. So we are actually cannot see the infrared, and visible light region is in this solar energy, from the solar energy. Therefore, we can see that UV visible light region is red, yellow, and so many colors that I've shown you before here. So we have so many colors here. These colors is under the visible light, okay, region. So for the infrared region, we cannot actually see through our naked eyes, and then unless they reflect some of the energy, okay. That material reflects the energy. So from here, we can actually find the peak wavelength or peak temperature at for that graph. So for example, we will use the wind displacement law here. This equation is important if you want to find what is the lambda maximum. So lambda T maximum power is equivalent to 897.8 micrometer per Kelvin. So for example, you want to find what is the lambda maximum for the temperature of 5800 Kelvin. Therefore, what you have to do, you have to substitute 5800 Kelvin into this equation. So lambda equal to 2897.8 micrometer dot Kelvin divided by 5800 Kelvin. So you will get what is the lambda maximum for the temperature of 5800 Kelvin. So lambda maximum, which means at this peak, what is the lambda? So wavelength here. Okay, we want to find what is the lambda maximum. If you want to see what is the temperature at the lambda maximum, maybe in the question will give you the lambda maximum for that temperature. Therefore, you will for example, the lambda maximum is 5 micrometer, for example. So you just substitute 5 micrometer and then you rearrange this equation to find what is temperature. Because this is in micrometer, therefore your lambda wavelength must be in micron meter unit. Okay. So we are often interested in the amount of radiation emitted over some wavelength band. So here we know that this graph is actually from 0 to infinity. Okay, we do not know where is the end of this graph. Okay. Therefore, we are interested at some point. We are interested at specified wavelength. For example, 0 to lambda 1 in here. This graph, for example, I take out a 100 Kelvin graph here. So we see this graph and then we take out, we bring it here. This is 100 Kelvin. So at 100 Kelvin, we know that if we calculate the equation to find what is the emissive power, spectral emissive power here, so this is actually from 0 to infinity. So, but we want to find what is the lambda, what is the emissive power for the specified wavelength. Okay. So we will use these kinds of equation. So EB, emissive power, for the black body from 0 to lambda 1, which means from this graph, this 100 Kelvin graph, we want to find what is the value for the emissive power from 0 to lambda 1, which means we will integrate this graph to find what is the area under the curve. So this is what we do. So we integrate the equation here. So that equation here, this equation, we will integrate it and then to get what is the value from 0 to lambda 1. So to find what is the area under the curve. So here, emissive power for the black body from 0 to lambda 1. For example, lambda 1, you want to find what is the emissive power for the black body from 0 to 100 micrometer. Okay. And then the temperature here, we know that this is graph for 100 Kelvin, right? So we will substitute at 100 Kelvin. So all this information, all this equation will substitute the value of 300 300 micrometer and 100 Kelvin, for example. And then this integration does not have a simple closed form solution. So if we integrate here, we have to have an advanced integration concept. Okay, therefore it is not a simple closed form solution. Therefore, what we do here, we will do a blackbody radiation function, what we call as a f lambda. So f lambda n at t, we will integrate the EB lambda, lambda t d lambda, this equation, and divide with the blackbody emissive power. So this blackbody emissive power is from 0 to infinity, am I right? So this equation is from 0 to infinity. Okay, therefore we try to find what is the fraction of this from the total this. Okay, understand? This is the EB lambda, lambda t. Okay, we have to find what is the total of this emissive power, and then by dividing this with this, we will get f lambda n, temperature at specified temperature, which means this graph is for 100 Kelvin. So lambda 100 Kelvin to the power of 4. So we have to find what is here. And n is equal to 1 or 2. Okay, f lambda 1 or f lambda 2. Now, you don't have to worry actually, but you have to know about this form. Okay, fraction form, blackbody radiation function form. What we will use is this table 12.2. This owner is already integrate for you and give you the f lambda. Okay, so what we do here, for example, if we want to find f lambda 1 at temperature, for example 100 Kelvin, and we have this kinds of form, so you must write down this kinds of form before you use this formula. Okay, to make sure that you understand this formula, this table comes from this formula. So here from this formula, we are actually wants to find from 0 here, from 0 to lambda 1. So we want to find what is the area of this graph under the curve, and then we will divide with the blackbody emissive power, lambda t to the power of 4. And then you do not have to integrate it, because this owner is already integrate you, and you will get this kinds of form, this kinds of table in your final exam if this kinds of equation, this kinds of question released to you, okay, in the final exam. So what you have to do here, we have lambda t. Take a look at here, lambda t, and we have f lambda here. So what you do is, we want to find f lambda 1 at 300 micron meter, for example. So 300 micron meter must be in micron, micron meter times with, this is graph for 100 Kelvin. So 300 times with 100, how much? You will get about 30,000. So take a look at this graph, this table. Take a look at the value of 30,000. Here, we have 30,000 here, lambda t. So this table can be divided into two, because this is the same. Lambda t, f lambda, lambda t, and f lambda. This is continuous. So from here to the 6,000 and 6,200 and to 100,000. So here we have 30,000, and take out the value of 0.995340. That is your f lambda 1 t. Okay, blackbody radiation function. And then if you want to find from 300 micrometer to 500 micrometer, for example, okay, 300 micrometer to 300 micrometer to 500 micrometer. So what is the blackbody radiation function? So what you have to do here, okay, we have this kinds of form. So f lambda 1 minus f lambda 2t equal to f lambda 2t minus f lambda 1t. So this is the form after we integrate it. So we know that the f lambda 1t, so we have f lambda 1 to f lambda 2, okay, at t. So we will find the value of 0 to lambda 2. So EB lambda, lambda t, d lambda over Stefan-Boltzmann t to the power of 4. So this is the first one. And then we minus with 0 to lambda 1. And you write down all the equation, okay, over Stefan-Boltzmann t to the power of 4. This is the same form. You just change it 0 to lambda 2 and 0 to lambda 1. So this kinds of form is actually the same as this one. So this is f lambda 2. And this one minus f lambda 1. Why minus? Okay. Now what we do here, from 0 to lambda 2, we are actually calculating the area under the curve for the fraction from 0 to lambda 2. So we have this graph. So we calculating, we integrate, and then we are actually calculating area under the curve from 0 to lambda 2. And then what we do after that, in order to find what is the value of lambda 1 to lambda 2, we have to calculate the value of 0 to lambda 1. So here at this point. So we will calculate the area under the curve here. So what we do when we minus f lambda 2 with f lambda 1, those area which intercept for both of this graph, for both of this function will be removed. So this interception will be removed, and then you will left the amount of area, the area under the curve for lambda 1 to lambda 2. So that's why this kinds of form is like this, okay? In order to find here, so from 0 to lambda 1, you will calculate the area under the curve. You have to minus with 0 to lambda 1 to find the area of this section, and then you will minus both of these values to get what is the value of this, okay? The same as if you want to find lambda 3. So you will find from, let's say we have another requirement to find what is lambda 3. So lambda 2 to lambda 3, for example. So you want to find what is the area here. What you have to do is to find f lambda 3 minus f lambda 2, because you have to calculate what is the area for the f lambda 3, and then minus with f lambda 2, you will remove the intersection area, and then you will remain the unintercept, okay, area. That's why we are using minus here. So again, from the integration, we know that the minus sign this will result to the minus sign, okay? So that is how we use the Blackbody radiation function. If you've been given this kinds of form, this kinds of graph, and that question asks you to find the Blackbody radiation function for 300 micrometer to 500 micrometer at the temperature of 5,800, you have to use these kinds of, if the question asks you to use Blackbody radiation function. If not, you have to find another ways on how to find the Blackbody emissive power. Because we have so many steps, so many equations to find the radiation properties, okay, radiation emissive power. So the radiative properties, so many materials encountered in practice, such as metals, wood, bricks, are opaque to thermal radiation, and radiation is considered to be surface phenomenon for such materials. So actually we have surface phenomenon and volumetric phenomenon. So to make it is, for you to understand about the radiation, we will use the surface phenomenon for the materials. If we are considering the volumetric phenomenon, so we have to take consideration of the volume of that material itself. So for example, if that material is in cubic form, so therefore you have to find what is the volumetric for that cubic form, and then you have to calculate the emissive power. So but right now we are only considering the surface phenomenon, so to make it easier for you to understand about the radiation and to calculate the radiation emissive power. So in these materials, thermal radiation is emitted or absorbed within the first few microns of the surface. So we know that the thermal radiation, the incident rays, will be absorbed, transmit, or emit. Okay, so some of these incident rays will be absorbed by the materials. So for example, if we have a glass and water, and it will exhibit different behaviors at different wavelength. For example, if we the incident rays or incident radiation is visible spectrum, so that materials for the glass and water we will see that the glass is a semi-transparent, and water also a semi-transparent, because the incident rays is in visible spectrum. So if we are strike that glass and water with infrared spectrum, so what we will see is the opaque surface. Okay, opaque surface. So opaque surface lah. Okay. And then I know that you already see the emissivity before this, because in the convection we have some radiation that will release from the surface of the body, okay, surface of the materials. And then the emissivity is actually the ratio of the radiation emitted by the surface at a given temperature to the radiation emitted by black body at the same temperature. So it is actually the ratio of the surface material at given temperature over black body emissive power. Okay, at specified temperature with the same temperature lah. So which means if the surface temperature is 500, and then the black body, the radiation that we calculated for the black body will be at 500 Kelvin. So next, the emissivity must be in 0 to 1, because it is a ratio. Then the ratio will be no more than 1. Okay, it is in between 0 to 1. There will be no emissivity 1.1, 1.2, no. It will be 0, 0.1, 0.5, and different materials will have different emissivity. And also, it depends on the wavelength, okay? And the last one is the direction of the emitted radiation. Okay, so this is not necessarily for you to understand about that derivation, because your level is not until the derivation is not in your subject. Okay, now we have to take a look at the gray and diffuse surface. So what does it means with diffuse surface? Diffuse surface is independent of direction. So as we can see here in this figure, we have theta, okay, 15 degree, 13 degree, 30 degree, 45 degree, 60 degree, 75 degree, and 90 degree. So if we say that diffuse surface, this conductor is directly proportional to the epsilon, so to the emissivity. Therefore, we will get the linear graph here. But at this point, the conductor and non-conductor is diffuse surfaces, which means that it is independent of direction. So as we can see here, as the data increases, the emissivity is not depends on this. Okay, as we can see here, the conductor will increase as the theta increases. At some peak, after the peak, it will decrease. So same goes as the non-conductor. We can see that this is not a linear, and it is not dependent on the theta itself. Okay, for the gray surface, surface properties are independent of wavelength. So from here we know that it is independent of direction, whereas for the gray surface it is independent of wavelength. So same goes as here, the explanation is the same. As the lambda is increases, so we can see that the epsilon is actually, so I say it as epsilon, it is represent the emissivity. So do not confuse this emissivity with the effectiveness. If you know, if you are calculating radiation function or radiative radiation energy, therefore this epsilon means that it is emissivity. When you are calculating, when you are using or you are calculating by using NTU method, this epsilon is actually represent the effectiveness. So it is totally different, and you have to differentiate between the emissivity and the effectiveness. So both of that in a different chapter. Okay. So this is the another other types of materials that it's not depends on the wavelength, diffuse and the gray surfaces. Okay. So now we go to the absorptivity, reflectivity and transmittivity. So as we can see here, we have incident rays. Okay, incident radiation strike through to the semi-transparent materials. We are not give you example for the opaque, since the opaque does not have transmissivity. Okay, if the semi-transparent, what we have here, when the incident rays strike to this surface, and then some of that rays will be reflected, and some of it will be absorbed, and some of it will be transmitted, and all of this will be calculated by using this equation lah. Okay, alpha is absorbed radiation over incident radiation. So G, absorptivity. ABS means absorptivity, not brake system. Okay, ABS is absorptivity, whereas for the incident radiation is G. So all of these will have G over G, and it depends on this G lah. So if we have reflectivity, then G here will represent G reflectivity. So alpha rho here is not density, it is reflectivity. So you must remember, this is not fluid mechanics, this is not chapter in fluid mechanics. Therefore, this rho is actually reflectivity. So this tau is not shear stress, it is transmissivity. Okay, so alpha, rho and transmissivity, tau. So the first law of thermodynamics requires the sum of absorbed, reflected and transmitted radiation be equal to incident radiation. So I'm so sorry because this goes to here. So G abs plus G reference plus G transmittivity. So absorptivity for G absorptivity plus G reflectivity plus G transmissivity is equal to G. So for the opaque surface, we know that if this material is opaque, so there will be no transmittivity. The energy, this incident rays will not transmit through the material. Therefore, tau here, transmissivity will be equal to 0. So this equation will become, so dividing each terms here, we will get alpha. So this position will be here actually, and this will be here. So I'm really sorry because this, I've changed the design of this slide. Therefore, the format is not in orderly manner. So G absolute plus G reference reflectivity, G absorptivity plus G reflectivity plus G transmissivity is equal to G. And then if we dividing each term with G, we will get that alpha. So dividing each of this term, G abs over G over G over G, and then this is over G. So G over G is 1, and then G transmissivity over G will be tau, and then G reflectivity over G will be rho, G absorptivity over G will be alpha. So alpha plus reflectivity, absorptivity plus reflectivity plus transmissivity is equal to 1. Now for the opaque surface, this is for semi-transparent, or transparent lah, okay, because transparent have the tau, okay, transmissivity. It can pass the light or incident rays can pass through the materials. So this tau will be we cannot equal to 0 this tau, since it is a semi-transparent or transparent. But for the opaque surface, this transmissivity will be equal to 0 because the light cannot pass through. Therefore, it will becomes alpha plus rho equal to 1. So absorptivity plus absorptivity, okay, plus reflectivity is equal to 1 for the opaque surface, okay. And then this is for the Kirchhoff law, that is this is all the derivation. So now we go to the Kirchhoff law. Consider a small body of surface area AS, emissivity and absorptivity at temperature T contained in large isothermal enclosure at the same temperature. So it is the same as what I've explained about the cavities, okay, before this snow, and then the last one is a large cavities. If the light pass through here, what will happen? It will strike to this or this material will emit energy. So it will emit energy and then it will go to the other side here, and then this side will absorb energy, and then it will emit the energy and it will goes to all these surfaces, okay. And then what will happen here, this Kirchhoff law states that after this what we call this derivation, we will get that the conclusion from the Kirchhoff law is actually the emissivity for these materials is equivalent to absorptivity. Whatever that material release energy, it will absorb totally by the other materials. But we have some condition that this Kirchhoff law is that this Kirchhoff law can be used. Okay, one restrictive condition. One, the surface irradiation correspond to emission from the black body, and then second, surface temperature is equal for the both of that materials. Okay, for both surfaces must have the same equal temperature. Okay, and it must be in steady state. Okay, so this relation is valid when the irradiation or emitted radiation is independent of direction, which means diffuse surfaces. Okay, so we will see these kinds of maybe we will see the use of Kirchhoff law in maybe in an example, the next example lah. Okay, thank you. That's all for the part for the first part, introduction, and after this we will go to the view factors. That view factors is the ways on how you calculate the black body emissive power in terms of the view. So we have a different rule that will be taken in order to solve that to solve the radiation question. Okay, thank you. Assalamualaikum.